Our next topic will be the transformer vector diagram of a loaded transformer. So when the secondary is loaded, the secondary current I2 is set up. The magnitude and phase of I2 with respect to V2 is determined by the characteristics of the load. So current I2 is in phase with V2 if load is non-inductive or it is a pure resistive. So it lags if load is inductive and it leads if the load is capacitive. The secondary current sets up its own MMF equal to N2I2 and hence its own flux 2, which is in opposition to the main primary flux, which is due to IO. The secondary ampere turns N2I2 are known as the demagnetizing ampere turns. So the opposing current flux 2 weakens the primary flux momentarily, hence primary back EMF E1 tends to be reduced. So for a moment, V1 gains the upper hand over E1 and hence causes more current to flow in primary. So let the additional primary current I2 prime is known as the load component of primary current. This current is antiphase with I2 prime. The additional primary MMF would be N1 I2 sets up its own flux, which is in opposition to flux 2 and is equal to it in magnitude. Hence the two cancel out. So we find that the magnitude or magnetic effects of secondary current I2 are immediately neutralized by the additional primary current I2 prime. So whatever the load conditions, the net flux passing through the core is approximately the same at no load. An important deduction is that due to constancy of core flux at all loads, the core loss is also practically the same under all conditions. So here we have the fluxes. Mutual flux to be the flux M, so flux that links both primary and secondary, this one. And primary leakage flux or flux L1, flux that cuts only in primary turns. So nandito siya, flux L1. Secondary leakage flux, flux that cuts only at the secondary turns. So Ix drops, voltage caused by leakage fluxes. The vector diagram of a loaded transformer, so this one, we have R1, X1, and our IO here is neglected. The current here composes of the IN and IL. So IN, since hindi siya na-draw dito, yung IN natin, or your IO, it is the sum of the Ix or the exciting current and the current at hysteresis and eddy current loss. Okay? So R1, primary resistance, X1 is the primary leakage resistance, R2 is the secondary resistance, this one. X2 is the secondary leakage reactance, I1 is the primary current, or ito, I2 is the secondary current taken by the load, V2 is the voltage across the load. So E1 is the induced EMF at primary and E2 is the induced EMF at secondary. So assume power factor of the load or unity. So unity means your load here is resistive. Okay, example, lamps, diba? Lamps are unity power factor or resistive loads. So what if we have a resistive load here? What will be its vector diagram? So how will we draw our vector diagram if we have a unity power factor load? So we will use the KVL equations or the Kirchhoff's voltage law here para ma-solve na, ma-formulate natin yung mga equations, and then we will draw its vector diagram. So, unahin natin dito sa secondary side of the transformer. Dito. So, as you can see, E2 will be the vector sum of, let's say, the R2X2 has an impedance of Z2 and it has a current for this circuit, I2, and we have an output voltage V2. So, para makuha natin yung E2, it is equal to the voltage drop at this impedance. So, I2 Z2 plus your V2. So, this is vectorially added. This is for the secondary of the transformer. So, how about naman sa primary? So, we will take a look at this outside of this circuit. So, simple lang, V1 is equal to the drop in impedance 1. So, I1, Z1, plus here, this will be your E1. So, simple lang yung equation. And also, our I.O. here, using KCL equation, I.O. will be IW for the current in the winding or in the resistance of the winding, plus the inductive reactance, which is I mu. So, depende na kung anong gagamitin nyo na subscript. Okay? So, if we will take a look again here, dito, so we will have V1, no, at this point, KCL, so I1 is equal to I.O. plus I2 prime. Next, i-draw na natin yung vector diagram dito muna sa secondary. So, we have, since our load is a unity power factor, our voltage and current will be in phase. So, here, the voltage and current will be in phase because it has a unity power factor load. And the drop in our R2, so that is I2, R2, since this is a resistive, it is also in phase with the current. So, this will be the I2, R2, and it has also a drop at our inductive reactance, I2, X2, and X2 is an inductive load, an inductive reactance, so 90 degrees with respect to our current. So, the voltage leads naman with respect to our current. So, current lags the voltage by 90 degrees, or voltage leads the current by 90 degrees. So, this will be our I2, X2. And the sum now of V2 plus I2, Z2, so this is our I2, Z2, I2, R2 plus I2, X2 is, this is I2, Z2. So, the sum of V and I2, Z2 is equal to this vector, which is your E2. Okay? So, the flux here, the main flux is perpendicular with respect to our E2. So, nandito yung flux, main flux. I mu naman is in phase with our main flux. So, nandito yung I mu natin. And also, since this is a resistive IW, so it is 90 degrees with respect to our I mu. This is our so this one will be your I1. And then, after we already get the vector of I1, dito naman tayo sa mga drop ng R1 and X1. For the drop of R1, we have I1 and R1. And again, this is a resistive, so our voltage here is in phase with our current. So let's say nandito yung this is our negative E1. This one, E1. It is just the opposite of your E2. This one will be your I1, R1. And the voltage drop at X1 is I1, X1, and it is 90 degrees, leading with respect to our voltage. So I1, X1 pala. So the sum of I1, Z1 plus E1, this is our E1, and our vectors I1 and R1, I1 and X1 is equal to V1. Okay? So this will be your vector diagram at unity power factor load. Next is the vector diagram of a lagging power factor load. So same procedure, ang nagkaiba lang ay yung current sa I2 is lagging. So we have the same circuit, schematic circuit diagram. We have the KVL equations. V1 is equal to I1 Z1 plus E1, and E2 is equal to I2 Z2 plus V2. They are added vectorially. So this is the vector diagram of a lagging power factor load. So here is our voltage V2 and current I2 is lagging, kaya nandito. And the drop in I2 R2 is in phase with the current. The drop in I2 X2 is 90 degrees with respect to current. The sum of the voltage V2, I2 R2, and I2 X2 is your E2. So this is E2 V2. With respect to E2, may flux tayo na 90 degrees. And then, it is in phase, yung I mu natin, this one, is in phase with the flux. And then, our IW here is 90 degrees with respect to I mu, this one. The sum of I mu and IW is your IO. And then, I2 prime is the opposite of I2. So, nandito siya, yung I2 prime. And I2 prime and IO is equal to I1. The sum of I2 prime and This one, IO is equal to I1. Next, the drop in I1, R1 is in phase with current I1. So V, the voltage drop, let's say V1 is in phase with I1. So nandito yung I1 X1, I mean this one, I1 R1. They are in phase. So this is our E1, the opposite of E2. And then the drop in I1 X1 is 90 degrees leading with respect to I1. The sum of E1 plus I1 R1 plus I1 X1 is equal now to our input voltage, which is your V1.